So supposedly by holding a coin out in front of them and finding out the point at which the coin fully obstructed the moon, they were able to get the angular dimension of the moon. And it came out to 108 to 1, which if you convert that from radians to arc minutes is what we're familiar with at about 31 arc minutes. And since we know one side of the triangle and two angles, a right angle and the other angle, we can now figure out the distance to the moon. And they were pretty close based on Earth diameters. They were also able to figure out or estimate the distance to the sun and this is Aristarchus, obviously a super genius from back then. He was able to give us a rough estimate of a distance to the sun. Now, he was very far off, but he still was able to establish that this is a very far distance. And the way he did that was he looked at the moon when it was at the quarter phase, because at the quarter phase, the moon and the sun make a perfect 90-degree angle. And he measured the distance from the Earth to the moon. And he came up with a rough number of 3 degrees. And again, since we know the distance from the Earth to the moon, that's one side, and we know two angles, the right angle and the 3-degree angle, or the 87-degree angle in this case, we can find out the distance d from the moon to the sun. Again, in either moon distances or Earth diameters. So now comes along a few years later, Eratosthenes of Cyrene, and says, hey boys, you need that diameter distance? No problem, I'll get it for you. And I'll only charge you a beer and the camel ride. And he knows, and Eratosthenes knew that there was a well at the city called Syene, which is not that far from today's Tropic of Cancer. So at the summer solstice, the sun was almost directly overhead. So he knew that at Syene, the sun was directly overhead. And he knew at that same day, or right around that same day, what the angle of the sun was at Alexandria. And so using basic mathematics and knowing the distance, and Alexandria was basically almost due north from Syene. He measured the distance from Alexandria to Syene, and so you got a partial part of the circumference of the Earth, and you knew the degrees, and you can, with basic math, you can figure out the whole circumference and the radius of the Earth. So as of about 200 BC, now that we knew the dimensions of the Earth, the radius of the Earth, we can now figure out the real dimensions of the distance to the moon and the estimated distance to the sun and the size of the moon, all in 200 BC. Now, this is where things basically stood for about the next 1700 years. And then in 1543, Nicholas Copernicus started making waves again in the field of astronomy, and things started to change, and we started to get new ideas. And Copernicus in 1543 developed the heliocentric model. And if you see Nicholas Copernicus' lifespan, it was 1473 to 1543. He basically published this on his deathbed, and it was basically published posthumously, although some of his close colleagues had the information a little bit sooner. Now, from Copernicus, the next jumping off point was Johannes Kepler. And Johannes Kepler believed in the Copernicus heliocentric model. And this equation here, Kepler's third law of planetary motion, basically was one of the most important findings in our history of astronomy, because this formula gave us the relative distances to all the planets. From this, we had the first step towards understanding the size of the solar system that we live in. And it's based on t squared is the period of the time of the orbit, and a squared is the radius of the orbit. And it was very easy relatively easy to measure over time the periods of the planets, especially the ones closer in. Saturn is, I think, is a 29-year period. So it's a little bit longer. But in any event, we were able to find that data, and we knew the relative distances because of Kepler's third law. So here we have to take a little bit of a sidetrack and understand the concept of parallax, because once Kepler had his equation, other people were now incentivized to try to find what that AU was, so that they can figure out the distances to all the planets. Because once you know the distance to the Earth, let me go back a slide, then you know the distances. Once you know the distance from Earth to the Sun, or even the distance from any one planet to another planet, from the Earth to Mars or Earth to Venus, you can figure out all the distances. And the main way that we started to figure out these distances is through parallax. And parallax is when an object appears at a different angle when you look at it at a different point in space. So even if you hold your finger up in front of you and you close one eye, it'll seem at a different angle than when you look at it with your other eye, because you're looking at it from a different angle. So if you look at a star from one side of Earth's orbit, it's going to look like it's going to have a different angle than when you look at it from another side of the orbit. And the concept of a parsec, which is a distance equal to 3.26 light years, is 1 AU subtended by 1 arc second of distance. Now, also an important part of getting to where we want to go as far as figuring out the distance to from the Earth to the Sun, we also needed a baseline for a measure of the Earth. And as I mentioned earlier, Aristophanes, back in the before Common Era times, had done a measurement. But in 1670, Jean Piccard got a much more accurate measurement using modern tools, basically tools that he developed that became more of a standard for surveying and measuring distances. And so here we are, 1670, we have a clear measurement of the size of the Earth, which is an important item that we need to know for future measurements. And the first person to get us to a close approximation for the distance from Earth to the Sun was Giovanni Cassini, and he did this by doing a parallax with Mars in 1672. And if you look on the left-hand side, hold on a second. This distance S is a known distance because Jean Piccard gave us accurate measurements of the distance of the Earth, of the size of the Earth. And so this was simply, once Cassini had one person in France, Cassini stayed in France, and I forget the name of the other person he worked with, Jean Rickner, I believe it was, or something like that, went to the southern hemisphere, to French Guiana, and he took a measurement there. And between Cassini's measurement in Paris and Jean's measurement from French Guiana, they were able to get an angle. And again, because we have two angles, a right angle and the known angle, and we have a distance, which was S, we were now able to find the distance to Mars. And using Kepler's third law, we know the distance from Earth to Mars, and therefore we knew the distance of Earth to the Sun. So 1672, we had a very close approximation of the distance of Earth to the Sun. And that gave us the size of the universe. Now, story continues a little bit because not everybody trusted the measurement. And famously, Edmund Halley, or famous for Halley's Comet, was not 100% sure, and he wanted to do a Venus transit check. And there was a Venus transit in around this time in 1600, but Edmund Halley didn't get good results. And so while this Cassini number was a good number, which as proven later at the time, it was a good number, but they weren't 100% sure. Also around this time, and this goes again to figuring out the distance from the Earth to the Sun and why it was important, in 1676, Ole Romer was the first to document that light had a speed associated with it. It wasn't instantaneous. Some of the ancient Greek philosophers thought that when you looked at something, something came out of your eyes, and that was how you saw something. Others thought, René Descartes around this time thought that light was instantaneous, but he was wrong. And Romer was not looking for the speed of light. Romer stumbled on the speed of light. So just give me 1 second here. Romer stumbled on the speed of light because Romer was investigating the motion, the orbit of Jupiter's moon Io, which is its most interior moon, and which orbits about once every 48 hours. And why was he investigating the orbit of Io? The orbit of Io was kind of like a natural universal clock. Anybody anywhere on Earth could look up and look at Io and basically get the time, or the same time that everybody else was looking at. And Galileo had proposed using the orbits of Jupiter's Galilean moons as a way of figuring out longitude, because you needed a universal time clock to know the longitude of where you are. Now, this method was primarily, well, at the time, they really wanted to find longitude for purposes of sailing and navigating. This method did not work very well on ships because it was very hard to pin down times using, if you're rocking and rolling on a ship. But it was very good for land-based observations, for measuring out boundaries and things like this. So there was an interest in getting the exact timing of Jupiter's Io motions. And one thing that Ole Romer found was that Sometimes it was 48 hours, sometimes it was 48 hours and 2 minutes, sometimes it was 47 hours and 58 minutes. It wasn't exactly always the same, and he wondered why that was. And he knew it couldn't be because of Io. And if you look here at this diagram, which is drawn by Romer, he surmised that when the Earth is moving along the distance either away in its when Earth is moving in its orbit away from Jupiter, like from L to K, the light then has to travel a little bit further from L to get from L to K to get to the Earth, and that extra time was a measure of Earth's was a measure of the speed of light. And similarly, if you're moving from F to G, when you measure it at F and then you go to G, now the light has to return a shorter distance and it's going to get to you a little bit faster. And Romer, with his observations, found that it took about 22 minutes to go the whole distance of the diameter of the Earth, diameter of Earth's orbit. And he estimated the speed of light to be around 226 kilometers per second. Now, this was not 100% accurate because some of Romer's measurements for Io were a little off. And at the time, the measure for the AU, the 1 AU, the distance to the sun, was a little off. Now, according to one source, and I didn't really see this other places, but Edmund Halley supposedly redid Romer's numbers and got a different time length that it would take for the diameter of the sun from 22 minutes down to 17 minutes, which gets you to a very close approximation for the real measure of the speed of light. But I was only found that in one source. But again, in any event, you need that AU, you need that measure of the distance from the Earth to the sun to get that accurate measurement for the speed of light. And also around this time, another person had measured the speed of light. This is James Bradley, and he was looking for stellar parallax. He wanted to see how the stars, he wanted to see the angle, the difference in the angle of stars from, say, March to 6 months later in September. And what he found was none of his numbers were matching up. And he was looking at a star that was basically due north of the ecliptic, so looking straight up. And it actually wouldn't be for another over 100 years before we did have the tools and equipment to actually measure the tiny stellar parallax numbers. But at the time, what James Bradley did stumble upon is what is called the aberration of light. So if Earth is moving in its orbit and you look at a star straight up, if you look at the diagram on the left here, if the Earth was just standing still, the rain would be falling straight down. But if you're in your orbit and you're looking up at a star straight above you, like the North Star, then the Earth is going to look like it's falling at an angle. And using, again, geometry and the aberration of light concept, James Bradley got within 1% of the speed of light, 1729. And again, he must have relied on the more accurate Cassini data for the Earth's distance from the Earth to the sun in order to get such an accurate speed of light measurement. Now, this was an accurate measurement, but there was no independent way to verify his number. And so that was another reason why this transit of Venus was important, because that would help give us an independent verification through the Ole-Romer method. Hold on a second. So Edmund Halley had tried to use the transit of Venus earlier on to get a measurement for the distance to the sun. It didn't really work. But he knew the next transit was going to be 1761, and then 8 years later, because Venus transits come in pairs of eight separated by 8 years. He knew the next one was 1761 and 1769, and he knew he wasn't going to be around for them. So he wrote a treatise on using parallax to use Venus transit and parallax to find the distance to the sun. Basically, he was saying, let me leave these idiots a roadmap so they don't screw it up when I'm not around. And so he prepared his summary, his treatise in 1716. Now, let's talk a little bit about Venus transits, because as I just said, they come in cycles. And they either separated by a gap of 121.5 years, or they're separated by a gap of 105 years. And each gap, there's an 8-year pairing. So if you look at December 1631, December 1639, then June 1761, June 1769, and then back to December, an 8-year gap. And then we recently had a gap in Venus transit in June of 2004 and June of 2012. I wasn't really into astronomy back then. I keep wondering what I was doing back then. How come I didn't look up at the sky then? But in any event, because these are rare, it was we had to get it right, and we had to take it seriously. And that was part of why Edmund Halley wrote that 1716 treatise, to make sure that we were all on the ball when the time came to get this important measurement. Now, how does the transit of Venus parallax work? So if you're, let's say, at the North Pole, and you look at the Venus transit on the sun, it's going to be at a different angle than if you're at the South Pole looking up, because you're going to be looking at it at different angles. So you could see the lines here that show how from different points of the Earth, you would see the transit on different parts of the sun. Now, the key to the observation data, what were they observing when they were, what did they need to observe in order to make their calculations? And so Edmund Halley said that we need to measure 4 things. We need to measure first contact, second contact, and then the time it takes to get to the third contact, and then fourth contact. Basically, we need the time from second to third, because that would tell us where we are on the transit line of the sun. And if we know that line and we know our altitude, we can then compare it to somebody else's altitude and their distance across the sun. And we can get that gap between T1 and T2, the vertical distance line. And this is an image of, this is actually from the 1769 Captain Cook voyage, an image of the transit setup. And when I was just mentioning, it was critical in getting the accurate timing from point 2 to point 3. And you could see they had to drag a pendulum clock, to wherever they were going to do their observation. So it was quite an endeavor. And Captain Cook was actually in Tahiti in 1769, and everybody else who went on there took an observation, who traveled somewhere for an observation, had to bring quite a bit of a setup. And you can see from the time these were observations, you get a sense of how they were measuring things and looking and recording the data. And again, the goal was, because we knew the relative distances based on periods between the planets, and we knew that Venus was 0.3 AU. As long as we got the distance to Venus, we could then get the distance to the sun and all the other planets. This is a sketch from a video I was watching. There's some great videos on this subject out there. And this again shows you a little bit more of the math involved. And like the same thing with Mars, one of the critical components is this distance here, which is basically the chord. So you can, because that we need two sides, we need one side and two angles. And that chord, which is halfway down, is the critical distance that we know from the size of the Earth. And once we knew our position, our latitudes on the Earth, we could then find that chord position. And then, as you can see, once we know that, we can just use the, as shown below, the R squared is proportional to T squared formula of Kepler's third law to get all our distances. Now, the first Venus transit in 1761, lots of parties went out from all different countries all over the world to try to find it, but it was kind of hampered because at that time in 1761, the major powers were in the midst of the 7 Years' War, kind of like the First World War of wars from back in the 1700s, and that caused some problems. And then this was the first time they encountered what was called the black drop effect, which was inherent in observing Venus. And that's where one of the critical measurements, the critical measurement was when at that contact point 2 to 3. The 2 to 3, when the Venus is inside the sun, it's not easy to determine when that point occurs, because it kind of like blends into the edge of the sun. Now, today we believe that that is because of the seeing conditions, atmospheric seeing. So if you look on the left-hand side, there's examples of Venus transit points in good seeing and bad seeing. You can see with the bad seeing, the black drop effect is greater, and on the bottom left, you can see it kind of blending into the edge of Venus' shadow, blending into the edge of the sun. It was also probably exacerbated by the fact that they didn't have the best optics back then as well. So the results of the 1761 transit data capture was basically a very wide margin of 77 million miles to 99 million miles. So it wasn't that good. And here are some actual recordings that people back then had drawn showing that black drop effect. The one on the left is Captain Cook from Tahiti in 1769. So in 1769 comes around, there was a real international effort. By this time, the 7 Years' War had ended, and people were thinking about other things. They were thinking about science, and they knew that this was their last opportunity for quite a while to get this data. And there was a real international effort. For instance, in Russia, Catherine the Great, the head of Russia, got personally involved, and she wanted to use it as a way of promoting Russia and saying that, hey, we're not just backward peasants who don't know anything, we're a real sophisticated society. And similarly with Benjamin Franklin was encouraging colony scientists for the same reason. You know, they wanted to show that America is not just a bunch of farmers. We're scientists here, and we're sophisticated people. Britain dispatched Captain Cook to Tahiti, and all the major powers sent multiple teams to collect data. there were about 130 observation teams that were sent all across the globe to record data. And in 1771, the French astronomer Jerome Lalande pulled together all the data from 1761, the data from 1769, and came up with a number of 153 million kilometers or 95 million miles, which is about only 2% off today's number. So he got pretty close. But the precision was not as precise as we had hoped because of the black drop effect. So, you know, it wasn't as precise as probably Edmund Halley was figuring we'd get, but we still got pretty close, and we were able to confirm the range of the data that we did have. And there were some interesting stories that grew out of the whole transit event, because people were sent all over the world, and traveling back then was a problem. And one interesting story, hold on a second, was that Guglielmo Le Gentile. So, and he traveled for the 1761 transit from France to the French colony of Pondicherry, which is in the southeastern side of off the coast of India. But because of the 7 Years' War, the British had captured the colony, and the British wouldn't let him land. So he missed the 1761 transit. But he figured he'd stick around for the 1769 transit and do some studies in the interim. And he got moved around a little bit. Manila, supposedly he was in Manila, and where the weather was very good. Then he got moved back to Pondicherry, where the weather's normally good. But lo and behold, after all of this time, and he built himself a nice observatory out there, day of the transit comes, and what do you know, he's got clouds. We all have to deal with that as astronomers. And right after the transit was done, the clouds passed. So he missed both transits. So now he figures, hey, let me go back to France, let me go home. It's been over 10 years. When he returns, he finds out that they declared him dead because he's been gone so long, they never heard from him. They sold all his assets, and his wife had remarried. So it was kind of you know, this was the trials and tribulations of some of the people chasing the Venus transit back then. Yeah, that was a detail that was in one of the papers that I read. I guess that was one of the quirks of French legal system back then. Yes,
Carl,
those damn lawyers.
Carl and Ken, I think someone in a prior ASLE presentation mentioned because he was gone for so long, they just assumed he was dead. So he was officially dead. I forget whose presentation mentioned that. Maybe Steve Lieber had mentioned something about that.
Yeah, so he was declared dead when he got back. He was found. He discovered he was declared dead, and his assets sold. Eventually, he actually lost his position at the academy, but eventually he got it back, and eventually he remarried. But that was a sacrifice he had made. So while the transit didn't give the precision that Edmund Halley, I believe, had thought that there would be, we still got, it was still an important measurement to make, and it confirmed the existing distance for the astronomical unit, which gave us the size of the solar system. It gave us the size of the sun. It gave us the speed of light. And it enabled us, even though we didn't have stellar parallax at the time, we were not that far off from getting to the point where we could do stellar parallax. And we needed a solid dimension for the astronomical unit in order to get the distances for stellar parallax. And as mentioned by one author on the subject, it also showed that people from various countries could come together for a common scientific purpose. And stellar parallax came a few years later in 1838, and Friedrich Bessel is credited with finding the first accurate measurement for a stellar parallax. The stellar parallax angle is extremely small. When he found one at 11.4 light years, and the parallax angle was only 2.86 arc seconds. And he had to use a special instrument called the heliometer telescope. And this is a list of improvements over the years for our astronomical units up until modern times. And you can see, up until Kepler didn't have a very close approximation. We started getting a better approximation in 1635 with Godfrey Wendelin, who measured that same angle that Aristarchus measured at three degrees. He was able to get a much closer measurement of that angle, and he got us a much closer for the AU. He's the first one who got us into the real range of 55 million. Christian Huygens is credited with a number, but a lot of people discount his number because he based it on a lot of guesswork assumptions. So people kind of consider it more of a lucky guess. But the real first time that we got solid numbers was 1672 and 1771 to get us a real close approximation for the distance to the sun. And similarly with speeds of light, it wasn't until 1729 when we got a really close approximation through James Bradley studying the aberration of light. And we weren't really able to confirm that accuracy for over 100 years until Leon Foucault, using his rotating mirror device, got a very close approximation. And then even then, there were other people coming up with other approximations, and it wasn't until the early 1900s that we really knew for sure what that number was. That's a good question, and that was one of the things I kind of wanted to look up, but I kind of ran out of time. I am not 100% sure, but it's I do want to dive into that at some point. And the same with the tooth wheel device. I started looking at that, the 1849 Hippolyte Fizeau device. I was trying to understand both those devices, and I kind of ran out of time before I could kind of figure it out, but I'll have to come back to you with that. And while we're on the speed of light, one very fascinating aspect of the speed of light is that in 1861, James Clerk Maxwell published his famous Maxwell equation. I think it was 1861 or 1863, around that time. And from Maxwell's equations, you could derive the speed of light. And Maxwell was studying magnetism, and he was studying electricity. His equations form the basis for our modern world of electricity. And we know now that light is electromagnetic waves. And using only the known constants of the permeability of magnetic field in a vacuum and the permittivity of an electric field in a vacuum, you can find the speed of light without any knowledge or observations of light itself. And someone once asked Einstein, what is it like to stand on the shoulders of Newton? And Einstein responded, I stand on the shoulders of Maxwell. Because Maxwell's equations gave the basis for Einstein. And actually, this equation right here was very important to Einstein, because what Einstein realized was that the speed of light is only a function of the inherent properties of the universe, of the permeability and the permittivity of electricity and magnetism. So when you shine a light, that speed is a function not of how fast the light is moving or whether it's standing still, but simply of the material itself that makes up the universe, like density or some other inherent quality of a product. And he used this to help formulate his ideas. And in modern times, we use radar to find distances to the planets. And in 1946, someone pointed a giant radar scope at the moon. This was the first time we used radar to measure an object in the solar system, and we got a very accurate measurement in 1946, the distance to the moon. And then in 1961, we were able to achieve a radar dimension, a radar to find a dimension to Venus. And that's how we do it in modern days. And that's it. If there are any questions, let me know. Oh, wait, hold on, let me give you the microphone.
I received a radio telescope in Puerto Rico. It was first time to detect the rotation of Mercury in 1965. They able to confirm the actual rotation by detecting the surface detail. And you can see kind of the rotation, so they confirmed that. So, yeah, that was great. We were taking within 59 days. Well, 58 days.
Because the planets are so small, they need a big telescope.
Yeah, so they used to wait on to bounce it off of the Earth's surface, and the resolution was high enough.
Yeah, I just wanted to mention one of my favorite books in modern times. It's a book by Bill Bryson called A Short History of Nearly Everything. He's a deeply researched and very humorous writer. And he goes into excruciating detail of the trials and tribulations of people who were participating in the observations for Venus. So if you want any more detail and very humorous detail, that's an excellent source. Bill Bryson. Yeah. Really.
Okay.
Carl, can you hear me?
Yeah.
Yeah, Carl, I
can hear you.
yeah, it felt like you were taking us inside the mind of the geniuses of the past. Great presentation.
Thank you.
Yeah, I wanted to say the same. It's just amazing. I really enjoy this. It's just amazing. The insights that these